Welcome back to the next topic that we're going to cover in our prologue unit. We're going to be talking about density. So right now in the work guide number 1, we are on density, slide 1 of 9. This video should be this video that I am recording right now, but in the moment, this is the example that's sitting here. Please make sure that you have an opportunity to watch this before you come into class. Have a nice set of headphones. The aim for this topic is going to be explain how density is related to the separation of air, water, and rock. So we're going to focus on how we can take this and elaborate on it later. Open up this link, go to page 29 in the PDF, and start to annotate. Maybe if you have a Google Doc open that you're taking your notes on, or you have your physical notebook that I'm hoping you have, you can start taking some annotations. Begin to read that now. Go ahead and pause and come back in a moment. Okay, so now that you've had a chance to annotate, maybe add some questions, maybe define some of the vocabulary in your own words, maybe you made even a drawing, let's talk a little bit about how density is important to all of earth science. And we're going to talk about the fundamentals first. So density, we're talking about the amount of stuff packed into a space. Sometimes it's a small space, sometimes it's a big space. Sometimes there's a lot of stuff in the space, sometimes there isn't a lot of stuff in the space. And that is going to affect the scale of where we sit on how dense something is. Okay? So in relative terms, we can be talking about something that is less dense or something that is more dense. In addition, we can also compare them subjectively relative to each other. All right, so when we're talking about something being more dense, we're talking about something that's tightly packed together. There's a lot stuffed inside whatever space we're dealing with. If we're less dense, we're talking about less stuff being put into a space. Usually we're discussing atoms, but we could even be talking about the people in this classroom. So last year, we had a lot more students in this space, so the room was more densely packed together. But now we have maybe less people here, so we are less dense in the same space, all right? So we're talking about spacing. Now, there's going to be a formula, which all of us should be aware of from page 1 of our reference tables. If you don't have your reference tables open, go ahead and click the link from the work guide to get you to page 1 so you can see your formulas. We are going to be focusing on that formula, which I have also highlighted for you here in your notes. So let's break down each aspect of the formula. So for mass, we're going to have units such as grams and kilograms. Those are going to be the most commonly referred to, and yes, they are metric. For volume, we will have milliliters and liters. Okay? For density, it is a combination of the two. So just like in rate of change, when we could not cancel two units, we left them together, we copied them and pasted them as they were formatted. So an example with grams above and milliliters below, we can copy and paste those into something like grams per milliliter. We may also have something like grams per liter. In earth science, we will be dominantly discussing most of our density values in grams per milliliter. Now, with that said, we also may see the occasional, and I'm going to put this in a different color, the occasional centimeter cubed, which is the actual measurement we use to create 1 milliliter. We literally had a box, a centimeter by centimeter by centimeter, filled it with water, said that's 1 milliliter. So you may see these switched out, but they are the same. So I made sure to put it there in the notes. Now let's talk a little bit about the formula and how we can manipulate the formula. So we have something here called the density triangle. And if we're trying to solve for density, we can cover up the D in this triangle, and it looks like M divided by V. Pretty simple, that's our formula. If we're looking for something like volume, we cover up the V, and we have M divided by D. Lastly, if we're looking for M, we will then have a D next to a V, and you can sort of imagine that these are like parentheses, And if they're in parentheses and next to each other, mathematically, we multiply them, which is what we do here when we cover up the M. So you'll see examples where you're going to manipulate the triangle and formula to get the values you need. Keep in mind that when you're solving for one of these variables, you might want to reference the types of units that only go with those variables so you don't get them mixed up. Now, here is a very interesting concept. It talks about just warming and cooling material and matter. And we have what I like to call earth science sign language. So if you all kind of work with me here, and I know this is usually the most awkward feeling because you're teenagers and you're all around each other, and maybe even in the comfort of your own home it may feel a little weird. If you have your hands about shoulder width apart, let's pretend each one of our fists represents stuff, aka matter. And between that matter, there is a distance. That distance represents our space or the volume. So right now we have two fists inside of our distance or volume between them, and this is our density. Now, if we were to get cold, maybe cool these things down, well, think about what it's like in the wintertime. When it's cold in the winter, you want to get close and bundle up and stay warm. Well, molecules want to do the same thing. They want to try to get closer together. So when we have two molecules, two pieces of matter, and it gets colder, they want to move closer together. So that space in between that volume decreases, meaning now we have the same amount of stuff but in a smaller space. So we're more packed together, meaning we're more dense. We come back to what I like to call the neutral position. We have our mass and we have our original starting volume. Now, if we were to get warm, think about summer, you don't want to go bundling up. You want to spread out, allow yourself to get the breeze to cool off. Well, you're spreading out and further away. Well, molecules do that too. Those molecules that are warmer tend to move further away. And as they move further away, you still may have the same amount of mass, my two fists, but the space, volume in between them has increased. So now they are less packed together, meaning they are now less dense. This concept and this example, this kinesthetic example, is going to be very helpful for you to understand density. My apologies for the computer choosing to interrupt us. All right, so down here, we have a few calculations that you can try out on your own, very simply manipulating the formula. So go ahead and pause up the video, try these out for a couple minutes, and then we'll come back and share the answers. Down here, I do have to make one change so that we can understand the concept a little better. And add in, instead, I would like to put 50 grams for the mass and 100 milliliters for the volume in this last example. So read through this, and then after you've calculated these, see if you might be able to label each of these with the state of matter of water. Which one might be ice, which one might be liquid, which one might be vapor. Go ahead and pause. So we're going to have 1 gram per milliliter. We're going to have here, if we calculate out, 0.67. And we're going to have grams per milliliter. And this last one, we're going to have 0.5 grams per milliliter. So now we have 3 different densities. Each is representing a state of matter for water. So of these, there's definitely one you can label based on the notes above. If you saw up above, you'll see that the rule for the density of water, liquid water, is going to be 1 gram per milliliter. You can also find that with your reference table, density of liquid water is going to be 1.0 grams per milliliter. So now we have to figure out which is ice and which is water vapor. So if you've ever put ice in a glass of water, you've seen that the ice floats to the top. So it means that it's going to be less dense than liquid because it's going to float. And I'm teaching you the property of having different densities and how they might layer themselves, those different materials. So if we think about ice, ice doesn't float up into the air, so it can't be less dense than air, but it's got to be less dense than liquid. So if we think gas would be the least dense, we then have to look and see which one of these numbers is lower. Well, this one is going to be lower, so this is going to be water vapor up into the air, leaving this one as being ice. So it's less dense than liquid, so it will float in liquid, but it's not less dense than air, aka it's more dense than air, so it's not going to float up. You don't see ice cubes float up into the air. So that leaves our last one here as being water vapor. Okay, so in this last one, what we have to talk about is how we have different samples of materials. So we have liquid water, we have rock, and then we have air, but the same volume. So each of these is 100 milliliters. So it's like saying we have 100 milliliters in our beaker of liquid water, we have 100 milliliters in our beaker of rock, and we have 100 milliliters of air, which doesn't look like anything because we can't see the air. And then we can calculate the density. So we're all got the same shape in our beaker, we all got the same volume in our beaker. And we're going to see how density changes because they're made of different stuff. We're going to see that we have equal volumes, but there are different materials in each of them filled up to the same volume, but because there's a different packing of matter, there's a different atomic arrangement of atoms in each of these, it's going to affect the density. Which leads me to a very important point. If an object, or if multiple objects, are made of the same material, they will equal the same density. No matter the shape, no matter the size, no matter any of that, as long as it's made of the same stuff. So if I have a piece of aluminum that's the size of a penny, and I have a piece of aluminum the size of the building, the atoms inside are arranged in the same spacing and order. But if I have something like wood and aluminum, they're made of different materials, they have different spacing of atoms inside, then the densities will be different. Okay, lastly, I'd like you to then move on to the next page, which is going to be our density guide practice. There are two questions. I'd like you to pause the video, try out these, and then we, as a class, will check in with each other before going over this. Okay, so you've had a chance to pause the video and hopefully try this out. This guided practice question lets me kind of know how much you know before, and then I'm going to also use it to teach you a method of taking volume. So the diagram below represents the mass and volume of a mineral sample being measured. These measurements were used to determine the density of the mineral sample. So here's our mineral sample. Here is a triple beam balance, like in the notes. Here is 2 graduated cylinders. So the triple beam balance will measure the mass. And then what we have here is a beginning volume on this graduated cylinder without the sample in it. And then we place the sample in it, and it's going to push or displace this water upwards by the exact amount that that sample is for a volume. So when we have 2 volumes, a beginning and an end, when we subtract them, we get the volume of the object, this mineral sample. So here we have 25 milliliters, here we have 35 milliliters, and there's going to be a difference. So the volume is going to equal 10 milliliters. That's the difference between the two of those. Over here, it's a little difficult to see, but that's where it has balanced the mass. We did not use any of the other beams to move over our masses, except this one, and it is 60 grams. So now we have our M, we have our V. Okay, we'll see you soon.